Yeah, we can hear you.
Okay, I'll start. Excuse me. Yes, can you see my screen?
Yep.
Okay, so good evening, everyone. I'm Mekon Joshi, and our team is from Kathmandu, Nepal. Uh, we are a group of undergraduate students studying electrical engineering in Tribuvan University, Pulchur campus. Before getting on with the presentation, first of all, I would like to thank the organizing team of this MagNet Challenge. The course that we are studying right now is more focused towards power system, and participating in the MagNet Challenge gave us a lot of insights and knowledge regarding power electronics and even machine learning. So we are really grateful for that.
Great. Thank
So
you.
uh, now, to explain what we did, I'll skip over the problems and background and go straight into the methodology. So, um, what we did is that in the data processing part, so the given data set consisted of 1024 samples of the B waveform for every cycle. So our first aim was to reduce that a number of samples, and we tried different things such as like downsampling the data and also aggregating it. And we found that using FFT, fast Fourier transform, to convert the time domain representation to into frequency domain representation gave the best result. So we used the DC offset value from the FFT and the subsequent 31 harmonics. So up to so a total of 32 terms instead of the original 1024, and we use that as the B data, as the B waveform data to train our model. So uh, then we also did a classification. So we classified the given waveforms into sinusoidal, triangular, and trapezoidal waves. And this was helpful because in some of the given data, the distribution was not same. So we did not have the same number of all categories of data. So in those cases, it was easier. It was helpful to classify the data because we could train with more even sample of data if we took the training sample according to the classification. So that helped us. Now, regarding the training and model, my teammate Dikshant will explain that.
Can everyone hear?
Yes.
All right. Hold on. Applications.
If you guys can, maybe you can turn on your camera. I guess it's good for us to see you for briefly. It doesn't have to.
So good afternoon, good evening, good morning to everyone that's present over here. Thank you so much for the organizing team for providing us with this opportunity to be here today with what we've done. So as my friend told before, the first thing we tried was to reduce the data, and one of the things that I remember right early on was when we got the data, we got it in the order of 3C90 and 3C94 and all that, and I opened the B field density CSV file for the 3C90, and my computer just froze, and we couldn't do anything. And then I called my friend and I said, like, what's happening? And his computer, his laptop had frozen as well because the CSV file was too large. We were not used to dealing with hundreds of megabytes of CSV files. So the first thing we kind of wanted to do was, how do we, this is not usable, we cannot do this, how do we reduce the data? And
Right.
so we tried different things. We tried averaging at different points, and we looked at different ways. And FFT, converting into frequency domain and just taking the first few harmonics, kind of gave us the best result. We knew that the performance would go down if we do not use as much points as possible, but that was just a sacrifice we had to make to move on.
Mhm.
So then we tried different, we tried to build a model, we tried different layers. And since we converted into frequency domain, we were no longer in time domain. We were kind of confused about whether to use LSTM or not. We wanted to use LSTM, but it's more common with time series. And we researched a little bit, we looked, and there were a few papers regarding using times like temporal dependencies for frequency domain training as well. So we kind of went with it. And yeah, we just added layers. We hyper-tuned. One of our main focuses was basically how do we reduce the training time, because uh, early on we tried to use all the points, and when we were using all the points, the training time was like few minutes per epoch, which was not sustainable. Like training 100 epochs would take multiple days at that point, and making even a small change would mean you got to start from zero. So our main objective was reducing the time, reducing the number of variables, number of input parameters that we give to the model, and try to make a single type of model that can kind of be used with the 10 materials that we had at the time. And we kind of used similar models, we used similar layers, and we got a pretty decent, I would say, results. They're not the best, but they're pretty decent. For some materials, it was kind of low. Like we went down to like 4%, 3% average. For some, like this one, 3C90, we like the distribution is kind of weird on this one, but we couldn't really figure out why this was. For some materials, it was working very nice. For some, it wasn't. And yeah, that's about it. And yeah, I think this is pretty much my friend kind of gave all the technical details. We kind of wanted to make it a bit informal, not go into the details exactly.
Mhm.
But yeah, this we kind of didn't really know much about machine learning, and this entire year was kind of a way for us to get into machine learning and maybe a little bit of deep learning as well. Not so much, but as much as we can. And I'm just happy that me, my team, just being students, and we were under a lot of academic like schedule pressure. We've got a lot of classes 6 days a week, so there was really not much time to do this, especially when it takes like hours and hours to train a single batch. So yeah, I'm just glad we kind of got the results into a proper shape.
Yeah, congratulations. This is like a big achievements, honestly,
Yeah,
for our
yeah,
students. Very
and I
impressive.
hope that we can learn a lot from different other teams' models, especially the ones that have done really well. And
Yep, yep, yep. I guess most teams are
yeah,
doing well. Most teams
yeah,
are better than where we started.
yeah.
Yep. Okay. Thank you. How about the testing? You showed the results for the training,
Right.
this other temperature. How about the testing
Yeah,
side?
right. These were the 10 different materials. Then we went to the testing, and for the testing, we didn't have the material data. Of course, there was no way to calculate errors. But in terms of training data that we divided, the results for D, we were expecting it to be quite bad because the number of data points was very. We were using a low number of data points, and the training data was also quite low. So it
Yeah.
kind of went out of bounds. So we
Right.
expected this one to be kind of bad.
Right.
B and C, we expected them to be decent because the amount of data given to us was quite a lot.
Mhm.
A was like it was in between. A and E kind of were in between. But E got overfit or something. Its error kind of went up in the testing set. It was doing kind of well over here, but it went up in the
Mhm.
testing set. So I
Yep.
guess it got overfit a bit.
Did you guys evaluate your models yourself yet or not? Not yet.
I did for E because I
Okay.
thought it was a bit too high, but then yeah, we got the same number as well.
Okay, great. Nice. Haran, Shukai, do you have any comments? Question?
Not really, but just for the previous one, the SAL, so one potential reason that I can see that they didn't really got a good result for the testing set is maybe you need to look into also the data normalization. So I was suspecting that when you do the data normalization for the testing set, there could be some mistakes there that mess up the coefficient that you use for the normalization. That's generally what we see when we found that there is quite a huge error in the testing set, I think.
Yeah. I guess Jacob, Haran was talking about.
Yeah, I heard. Yeah, we're gonna look into it because it's super weird. Or maybe we missed it and we just overfitted super hard, and we basically learned by heart the whole data set. And now, of course, if we have a fully new data set without any, but I should have split it properly. So I don't.
Yeah,
we look into it. Not sure yet.
We're saying like during the normalization process, there could be a parameter mismatch, but we don't. You guys can check.
Yeah.
Or maybe you can talk offline. Now we can freely talk about it.
Yeah.
Yeah.
So yeah, the previous team had also done FFT, so it was kind of we've kind of done the same thing, not same but similar things. Similar approach, I should say.
Like FFT is the first thing, first reaction when you are trying to compress the data. Yeah, we understand they are different. So fundamentally, right now everyone is talking about large language model, making a model large in the long term. It's fine because computers are getting better and better. But for us, we think it's useful to make sure we compress the model and develop a compact model, and that sort of help. So help with the computer.
Yeah, I guess
you mentioned.
Yeah, I guess we need to learn a lot about how to kind of manage the data before we can reduce the model. Right. So instead of smashing everything, it kind of needs to go in a flow or something like that. So we're learning, basically, we're still learning, and hopefully we'll learn from other teams more than,
Yep. Great. Nice.
Yeah. And thank you so much.
Yep. Thank you. Stay engaged. So yeah, we'll open source the data that the models and data, and I'm sure the best model is to come. Like it's not there yet. Once we learn from each other. Yep. So okay, let's move on to the third team, Bristol.